Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, and this is lecture number 50 where we design or we give you the properties of qubits. In the outline we will look into the superposition, which we have already taken up in the previous lecture. We will look into entanglement, then cloning or copying of qubits, collapse of one of the state post measurement, and you can have infinite number of states as a qubit, and they are highly susceptible to noise. We will see how it is compared to an ordinary design, right. This is what we are looking into as far as this state is concerned. Let us come to quantum superposition principle. Quantum superposition, as the name suggests, is basically stating that a qubit can exist in multiple number of states at once, right, which means that, as I discussed with you in the previous lecture, that a single state psi can be represented as this, as alpha and beta, where are basically the functions which are there with us, and these functions are very unlike a classical bit, right. It is not like a classical bit, okay. And this comes from the linearity of the concept of quantum mechanics, and this can be given by this expression which you see. So basically when I say psi equals to alpha ket 0 plus beta ket 1 is basically a coherent superposition. So this is basically known as coherent superposition. Coherence is essential for a qubit to be in the superposition state, right. And with interaction, quantum noise and decoherence, it is possible to put the qubit in a mixed state, a mixture of combination of incoherent mixtures of multiple states, right, multiple states available. So there is an incoherent mixture which can happen, and this implies that there will be always a superposition principle. If you look at the left hand side, if you look at bits versus qubits change, on the left hand side the classical computer is represented by a 1 or a 0, and these are therefore very specific off and on state, whereas for a qubit it can be 0 as well as 1 and 0 here. This is 0 and this is 1, but there will be a state which will be a combination of 1 and 0, and that is the reason we have written here that qubits can take multiple values simultaneously, and that gives me enough longevity in terms of the amount of possibility of parallel calculations available, because there are multiple states available very fixed in the calculation. So a quantum logic gate, if you want to find out, is basically the building block. So for any quantum circuit we need to have what is known as a quantum logic gate, right. We will discuss this in detail in a later case, but typically you should know that there are quantum logical gates which operate on qubits, right, and they basically do a unity transformation or a reversal in qubit can take place, and you can have multiplication of two states can give you a third state for the qubits, right, and that is the majority of case that you will get multiple states available to us by doing manipulation in these terms. Now quantum measurement is basically an irreversible operation. So if you look at quantum states, quantum measurement, if you look, it is basically irreversible property, alright, and in which the information is gained about the state of the single state and the coherence is lost. So I get the information for the state, and the coherence is lost, and the qubit itself loses its state in a sense. We have also seen that measurement of the state of the qubit also alters the magnitude of alpha and beta, which we have seen in our earlier discussion, right. So if alpha is changed to 0 and beta is changed to 1, it implies that a ket 1 will come into picture and the output vector corresponding will be 0 1, and vice versa. If alpha equals to 1 and beta equals to 0, the output will be basically 1 0, which will be coming in the output side. And this is, so if the measurement is performed on a qubit that is, let us suppose, entangled, we will discuss this in a much more detailed manner, entangled, the measurement may collapse the state of other entangled qubits. So once you are able to, entanglements, if you look at the two qubit states, they are entangled in a sense, they are not separate states. In the superposition state they are always entangled. So if you want to change one of them, the other changes drastically its point, and that is one of the major ideas of entanglement, which we will discuss later on. So that is what I was coming to. So this is entanglement is a very strange operation of quantum connection between two particles, that the state of one instantly tells you something about the other even if they are far apart, which means that if I have one state here, as you can see in the cartoon shown below, that let us imagine that one state is in Earth and another state is in the moon, then there are two coins, for example, I can say, and they are magically linked such that the flipping of coin at Earth here, you can extract the value of the state of the coin at the moon. Then they are entangled through each other through a quantum state, and therefore there will be an instant change in its state as you flip the coin in the Earth. And this property is only exclusive to entangled bits, in qubits especially. It is not in your ordinary bits in computer, which means that if 1 0 changes here, does not necessarily mean that somewhere else 1 0 or a 0 to 1 will change. That is shown also by this cartoon on the right hand side, which is shown here. So, which means that if I say that opposite must happen, then if 1 is red, then the 2 must be blue, which means that there are two states, red and blue. So, if at one Earth you have red and we say that it is entangled with a quantum state and the moon, then the opposite will happen. Then we say that in the moon it is state 2 is a blue state. The reverse will be also, this is almost saying is alpha equals to 1 and beta equals to 0. In the second case, I can say that if you are getting, if 1 is blue, then obviously you will get 2 as the red sign in the external world. This is entanglement, which is mean that two states are quantum coupled in space and time, right. They are, though they are far apart, it effectively means that anything happening at the Earth, you influence the state of the entangled bit, and distance is not the problem, it can be done at any point of time, right. And since the information can travel at the speed of light, you will automatically instantly see a change in the quantum bit qubit state. Now, if you have an unknown qubit, you possibly cannot make an exact copy of it, right, and it is not possible as such. As you can see in the cartoon here, if you have this cat here, you cannot, it is very difficult to make a copy, right. In normal world it is relatively easy, right. For example, you can copy a file and even a document, right, and bit 0 can be easily converted to bit 0 and 1 to 1, and we already know in file we always doing it in a word file, control C and control V. It is very easy. When you actually do it, the same bits are repeated, right. In quantum world you cannot copy a qubit in an arbitrary state, and therefore you cannot just copy and paste the qubit. That is where the encryption, or that is where the security of the world comes into picture. Security of any quantum communication system comes into picture, where you just cannot copy paste qubits, right. You cannot just paste and copy qubits, and therefore it's because, and the reason is very simple, because once you try to do that, once you try to do a sort of a copy paste action, you end up changing the state of the qubit, and therefore pasting is very difficult in a sense. Copy pasting is very difficult, right, and it changes the state of the world. Okay, let us look at the measurement point of view from the qubits, right. Unlike classical systems where the observation just, so basically in a classical system means when you are doing, let us say a classical computer, right, and you are reading the bits from the memory. So what you are doing, you are reading from the memory, right, in the states in the quantum state, and the measurement changes the. So what is happening is, in the quantum state the measurement actually changes the state, as I discussed with you. So before measurement, before the measurement you try to do, the qubits have many possibilities. After the measurement, the qubit has only one state available and is decided by the measurement itself, and that is the problem, which basically means that the way you do the measurement, that tries to influence the state of the qubit rather than the qubit state being known to me. In classical world, how you do the measurement in most of the cases do not change the state of the bit. So if you want to read a bit, a 0 or a 1 from a system, you can easily do that in a very easy sense of manner, right. So let us take it, how do you do an analogy? Let us look at the analogy from the outcome. So let us have a box and with two cards A and B. The cards are hidden, mixed, and in a quantum world the box is both A and B at once, right. Now in quantum world, in classical world, if you put your hand inside the box and try to open it, if it is a A will come out, if it is a B card will come out, right. But in the quantum world, the very act of opening the box will decide the state of A and B, right. and that is the problem area as far as measurement is concerned. As I discussed with you, qubits can have infinite states effectively. So, bits have two possible states as I discussed with you, 0 and 1 lighten, but qubits can have multiple states 0 and 1, and it is basically the arbitrary state of a qubit is given by alpha times ket 0 plus beta times ket 1, such that mod of alpha square plus mod of beta square is equal to 1, which means that alpha and beta have infinite number of states available, and that will give me the variations of alpha with the boundary condition that alpha square plus beta square equals to 1. I can have infinite values of alpha and beta, which gives me infinite number of states for psi, and I can have infinite possible qubit states available to me. Obviously, qubits are highly susceptible to noise. When I say noise, I mean to say electrical noise. Now, if you look at the bits and if you look at the quantum bits, let's do a one-to-one correspondence between that. So, as I discussed with you, a bit is either 0 or 1, and even if there is some noise, there are some thresholds below which if the noise is there, we can ignore those small fluctuations, and a 0 will be read as 0 and a 1 will be read as 1. There is no problem in the noise. Say for example, in this state of our example, even if it is 4.9, if I say 5 volt corresponds to 1 and 0 volts corresponds to 0, and if I keep my thresholds at 2.5, any voltage above 2.5 will be still read as 1, and any voltage below 2.5 will be still read as 0, right. And therefore, it is very easy to store, obviously, because you are storing zeros and ones, and it can reliably transmit the data from point A to point B without, even if the noise is being inserted, you know there will be heavy noise rejection in classical domain, right. And that's so, and even if there is a noise available with you, you can actually do some error correction in the noise and find the factual value at the receiver end. However, let us look at the quantum state. A qubit is a quantum state, as I discussed with you. Even if there is a small noise, be it from temperature fluctuations, electromagnetic radiations or thermal vibrations, what will happen is alpha and beta will suddenly change, and as a result there will be the collapse of the qubit. So, you had say alpha equals to 0.5, beta equals to 0.5, then I will have my psi, ket psi as equals to 0.5 ket 0 plus 0.5 ket 1, right. Now, if there is some noise, this suddenly changes state. So, this is 0.3, let us suppose, and this becomes point something, right, such that, but you need to ensure that this square plus this square will be equals to 1. If you ensure that, and but within those boundary conditions, with a small change, you will see a sudden change in the value of the psi, and this causes decoherence or the loss of quantum behavior, right, and that is possible when you have an external electromagnetic radiation, vibration or a variation in the temperature. So, to quickly, what we learned till now was, we learned into the various concepts of design. Various concepts we had learned was, we had give you a brief idea about the idea of alpha, beta and how this is related to the value of psi. We looked into the difference between qubit and bits, right, bits. We also looked into the concept of decoherence, coherence, and I gave you a brief insight into entanglement as such, right, entanglement. Now, we go to the next case, and we will quickly, so we will quickly use quantum computer architecture as such and give you an outline of the temperature based stack and then the functional stack. So, the first is the temperature based stack. So, this now we are entering into the hardware part of quantum computing, where we use temperature based stacks and functional stacks as such. Block diagram we will be using. Now, so this is a temperature based stack, how using temperature changes we are able to find out the value of the qubit coherence. Now, quantum computers are operating, as you all know, and I have discussed with you, that it works in cryogenics temperature, which means that ultra low temperature is there, and to maintain qubit coherence, and also to why. So, when you maintain a very low temperature, there are no thermal fluctuations, you ensure that there are no thermal issues available, you also minimize the thermal noise, and therefore, you need to store these data qubits at very low temperatures, somewhere around millikelvin region, right. Now, let's go. So, look at the left hand side diagram, which is diagram number A. This gives you a stack, a temperature stack for typical quantum computer, and if you look at 300 Kelvin is basically the room temperature, and it hosts the conventional electronics, not the readout circuitry, but the conventional electronics, right. And then these are responsible for high level tasks, for example, application control, software and algorithm execution, all this takes place at this stack here, right. And let's look at the next stack, and which is somewhere, so this is 300 Kelvin which we say, then this is the point which we are talking about, right. And this stack is what is known as an intermediate cooling stage and can host parts of certain amplifiers and cryogenic control. So, my cryogenic control sits effectively at around 4.2 to 4.5 Kelvin range, up to 10 Kelvin range it sits very easily, right. And from 0.8 to 0.1 Kelvin, these circuits are not only physically close to the qubits, but they are in temperature gradient also relatively closer, though they are of 2 orders of magnitude higher temperature as compared to your qubits. What we use for is primarily used for routing, multiplexing and signal processing. So, somewhere around this particular point, right. This is the point which we are referring to, 0.8 to 0.1. This is one which we are referring as 50 Kelvin to 3.5 Kelvin, this one. So, we are going down and down in temperature as we move ahead, right. Now, if we go to the last temperature stack, maybe the lowest temperature stage, this is where the physical qubits are stored, right, which is where somewhere here in this box, right. This box is 20 millikelvin stored is there, and this is the lowest energy state which happens, and this hosts physical qubits. And for example, a superconducting qubit or even spintronics based qubits get stored here. And the problem with this whole dilution, this is known as a dilution refrigerator, the whole block, there will be a big vacuum chamber which will be available, but we will not go into details. But for this chamber to maintain at 20 millikelvin, you require very good thermal isolation, and that is one of the challenges of designing such thermal stacks, that how to design such that you are able to isolate the temperature inside the qubits from the external world, right. And that is what the temperature stack control is. Let us look at the functional stack now. So, we looked into the temperature stack, temperature was 300, and if we look carefully, it is 300, we went down to 50 to 3.5 is the conventional electronics, 3.5 down to 0.8 is where you store certain readout circuitry very close to the qubit, around 20 millikelvin is the point where you are actually storing the data. So, if you look from milli to 300 Kelvin, there are 5 orders of difference in the temperature. So, there is a big thermal gradient which happens between this point and this point, but then we need to ensure that these thermal gradients do not appear, because otherwise you will be transferring heat from the conventional side, which is 300 Kelvin down below. So, there are proper thermal isolations being done at each stage in order to sustain and maintain a particular temperature. So, this is the temperature stack which we are referring to. Let us come to the functional stack. The functional stack basically consists of the block D, and if we go step by step, then the control, readout and routing and multiplexing, which is this stack, is where you do the electronics part, right. This is the electronics part. This is the application of the control signal and algorithms part, and this is where you have quantum devices being stored. So, there are 3 typical part of the stacks, functional stacks available to us. One is where you store your physical qubits, that is where is the heart of the quantum system. It will have qubits, couplers and quantum gates. Above that you will have control and routing and multiplexing organization, again readout circuitry, and above that you will have the application stack, software and control circuits. So, let me again quickly recapitulate what we did is that we gave you an idea about the temperature stack in this paper, in this temperature stack, and we also looked into the functional stack. We looked into the functional stack. So, these 2 stacks we looked. We also, when we discussing this, we saw that our qubits are placed at millikelvin, right, and my functional stack, the lowest stack which is devices, is at, this is where you kept your devices, right, from around 4 to 10 Kelvin where you keep your readout circuitry and other places, and anything above that will be responsible for keeping the other parts of the system. And the functional stack, the devices are at millikelvin, then all your multiplexing and routing algorithms, routing methodologies are in 10 Kelvin, and anything above that is the software, control, application domain are all kept there, right. So, let me quickly give you a brief idea about now the cryogenic CMOS circuitry, architecture of controller, we will look into it. We will also go into the CMOS readout circuitry, and then signal processing and cryogenic CMOS circuitry, which we will look into. Now, basically there is an issue here which one needs to understand as far as quantum computer is concerned, that there is a region of interfacing between the quantum world and the classical world. 300 Kelvin is where your classical world is there, right, and where all your classical sorts of methodologies, you will still have bits available to you. But as you go down the temperature stack, and especially at qubits range, you will always have a qubit nature, and therefore my quantum processor is kept somewhere around 1 Kelvin or less than 1 Kelvin, and my classical controller is kept somewhere at 300 Kelvin, right. And therefore, the classical controller controls the qubit from where I am able to read out, and the classical controller is able to get the state of the qubit by doing some amount of insertion of certain signals, so that you are able to sustain this value of quantum computing values, right. Let us look at one by one, and if you look at the quantum processor working at 1 Kelvin or below, they operate at cryogenic temperatures, very low millikelvin range, execute quantum operations on qubits, and they require very precise control and timing to maintain coherence. And that is the challenge which you face, that the timing issues and control has to be so precise that the state itself does not get destroyed while reading it. Whereas in classical controller, on the left hand side, if you see, it sends control signals, right. It can send an optical signal, it can send a microwave signal, and so on and so forth, to manipulate the qubit state. Then from there it receives a readout signal, right, from the quantum processor, and that is what is read. So, these are the measurement results which you get from the quantum processor output, and then they perform certain measurements and then do an error correction at the classical controller interface, right. Now, the communication is basically bidirectional in nature. Bidirectional, when I say, I mean to say that that it is both ways communication which you see. That means quantum actually gives output to the classical is able to do a readout on the quantum. Now, the classical computer basically programs the quantum gates and sequences in order to ensure that you get the output properly, and in the readout path, quantum processor returns measurement data post the computation. Once the computation has been done, the quantum processor returns the measured data to the classical controller. This is the basic cryogenic CMOS circuit, cryo-CMOS output, and it has been taken from a very nice paper, and it appears as a brief in some journal. Have a look into this journal, and this is the very basic block diagram of a cryogenic CMOS circuits and systems. This 300 Kelvin is where your classical computers are all sitting. I have digital and ASIC digital blocks where you insert the logic, and this is sitting at 4 Kelvin. We have a readout circuitry, we have a control circuitry, and we have an auxiliary circuitry. So, these three circuitries are part of the readout part, right, and they are part of the overall readout network of the design. So, and of course, the final one comes at 2200 millikelvin, and where we are sitting the quantum processor, we have a mux and a demux, optical guide, and so on and so forth, and these are sitting at millikelvin. So, what we will do in our next lecture is start sending you brief logic of all these operations in a detailed manner. So, let me recapitulate what we studied till now. We actually looked into the architecture, quantum architecture here, and we saw that the classical architecture is sitting at 300 and the quantum architecture is sitting somewhere around few millikelvins to maybe 4 to 10 kelvins, right. This is where your devices are kept, quantum devices are kept. This is where your readout and auxiliary circuits are kept, right. What you should be therefore aware of in coming weeks or coming days is how we are going to read a state of a qubit. That is what we are trying to do in the subsequent lectures, right. I hope you enjoyed the lecture. Till we meet next time, goodbye.